In this video, we discuss learning outcome number 3 from lesson 6.4, which is all about combining the rare event rule for inferential statistics with the central limit theorem to compute and interpret low probabilities. So here is the rare event rule again. It says, if under a given assumption, the probability of a particular observed event is very small, and then the observed event occurs significantly less often or more often than what we would typically expect given that assumption, then we conclude that the assumption is probably not correct. So let's dissect this a little bit. It says, if under a given assumption, so we're assuming something is true. Say, assuming something is true, the probability of this particular observed event is very small, very unlikely to happen. If we have that assumption and we know that the probability is supposed to be very small, but then the observed event occurs significantly less often or more often than what we would expect, we usually say, okay, well, if this is happening so much more often or so much less often than we would expect, maybe our assumption was wrong. We can conclude that that assumption is probably not correct. That's the rare event rule. So if something has a very low probability, then if it's happening much more often or much less often than we would expect, we might say, maybe that assumption is wrong. This is one of the most important rules of statistics. It plays an essential role in hypothesis testing, which we're going to talk about more in chapters 8 and 9. And this is going to influence how we interpret the probabilities that we come up with using the central limit theorem. So we'll find that if a probability happens to be very low, that rare event rule is going to influence our interpretation of the probability. If the probability is very low, but this event that we actually observe is happening much more often than that probability might suggest, we might say our original assumptions must be wrong. Let's rewrite the assumptions. So in other words, statisticians are going to reject explanations based on very low probabilities. So if we say that is so unlikely to happen, but it's happening, well, then chances are the assumption that said that it was unlikely to happen is wrong. It's incorrect. There must be some other assumption that we should make that would more accurately explain what's going on. So here's an example. It's an example about elevator safety, It says, when rating elevators, it's common to use a 25% safety factor so that the elevator should actually be able to carry a load that's 25% greater than the stated limit. So let's say an elevator has a maximum capacity of 4,000 pounds. Well, that will become 5,000 pounds after we increase the weight by 25%. So even though it says 4,000 pounds, it can actually handle 5,000 pounds. Now, we're asked to assume that the weights of males are normally distributed with an outdated mean of 174 pounds and a standard deviation of 39 pounds. So we're going to make this assumption, but it's probably not a good idea to make this assumption because this mean is outdated. Men don't weigh an average of 174 pounds anymore. More recently, it was found that the mean weight of males was closer to 189 pounds. The question says this: if an elevator is loaded with 27 male passengers, find the probability that it is overloaded because they have a mean weight that's greater than that 5,000 divided by the 27 passengers. It's approximately 185 pounds. The question says, does the elevator appear to be safe? Okay. Now, let's go back to that slide. Let's focus on the question they ask us. If an elevator is loaded with 27 male passengers, so n equals 27, find the probability that it is overloaded because they have a mean weight greater than 185 pounds. So we want the probability that the mean is greater than 185, given that we have n equals 27 male passengers here. So we were told at the very beginning that the weights of men were normally distributed. Since the weights of men are normally distributed, the sample means of the sample size n equals 27 are also normally distributed. And the mean of the sample means is equal to the mean of the population, which is 174 pounds. And the standard deviation of the sample means turns out to be the standard deviation of the original population, that was 39 pounds, divided by the square root of the sample size. The sample size was 27 in this case, so that quotient turns out to be about 7.51. So if I want to find the probability that a sample mean is greater than 185, the first thing that I'll do is I'll sketch a normal distribution. Now this will be a normal distribution for the sample means, not a normal distribution for the weights of men in general. This is the normal distribution for the sample means when you're dealing with a sample of size n equals 27. Now that sample will have a mean given by this mean of the sample means 174 pounds and a standard deviation of this standard deviation of the sample means, which is at approximately 7.51. So we'll sketch that normal distribution and then we'll graph 185 pounds. And then since we're interested in the probability that the mean is more than 185 pounds, so that means we've overloaded our elevator, we're going to shade to the right. So we might have a graph that looks like this, and let me hover over it. This was created on mathcracker.com/normal-probability-grapher. If you follow that link, you can graph normal distributions and shade them as well. Okay, so we sketched a normal distribution with the appropriate mean and standard deviation. We graph x bar equals 185 pounds. Again, that's a sample mean of 185 pounds. And we're asking ourselves, what's the probability that this elevator is overloaded? Or alternatively, what's the probability that the mean weight of those 27 men is more than 185 pounds? And then we want to find that probability, which corresponds to this area, this red area in our graph, using table A2 if we want to, or using Excel. Okay, so I'm going to show you how to do this both ways. With table A2, this is what we do. The first thing we do is we take our x value of 185 on that boundary there, and we convert it to the appropriate z-score. And then we use table A2 to find the area to the left. And then we'll take 1 minus the area to the left to get the area to the right. So first we compute the z-score this way. X bar, that's 185. So that's the sample mean. Then we're subtracting the mean of the sample means, which happens to be the same as the population mean. And we're dividing by the standard deviation of the sample means, which happens to be the population mean divided by the square root of the sample size. We just substitute everything in and we get a z-score of approximately 1.47. So this z-score, or this x value of 185 pounds, given that the mean is 174 pounds from that dated data that we started with, given that that's true, this standard, or this x value, or this sample mean of 185 pounds is 1.47 standard deviations above the mean. Then if I want the probability that our mean is greater than 185 pounds, that's approximately equal to the probability that z is greater than 1.47 pounds. It's an approximation because this is an approximation over here. Now, I won't find the area to the right in table A2. So if I want the area to the right, I have to find the area to the left first. And then I'll subtract the area to the left from 1 to get the area to the right. So let's go to our z-scores. And I believe it was 1.47. So I go to the positive z-scores. Then I go to 1.4 over here. That's 1.40, 1.41, 1.42, 3, 4, 5, 6, 7. And then I don't know if you can see it, but 1.47 is right here. That gives us a probability, or an area to the left, of 0.9292. Okay, so then we want area to the right. And that is approximately 0.0708. So there's 7% chance approximately that elevator would be overloaded when we have 27 men that enter that elevator. Now that's using table A2, and that's based on an approximation of this z-score. We can get a better estimate of this probability if we use technology. So we're going to use Excel next. Here we want to use Excel. This time we'll use the normal distribution function. It's norm.dist, and then in parentheses you're going to add some arguments. So you'll have the x value, the mean of this distribution over here. Then you'll also want to use the standard deviation of this distribution. Now make sure that you use the standard deviation of the sample means, not the standard deviation of the original population. The standard deviation of the sample means is that 39 over the square root of 27, which is approximately 7.51. So let's look this up now. Or not look it up, but find it. So I type equals norm.dist, open parentheses. The x value is 185. The mean, I'm assuming, is 174. The standard deviation is approximately 7.51, and we want to say true for area to the left. And that gives us about 0.9285. That's the area to the left. I want the area to the right. So I'll take 1 minus the area to the left to get the area to the right. So it's about 0.0715 approximately. And that's what we have on our slide here. Now this is slightly better, slightly more accurate than the answer that we found using table A2. Okay, so now let's interpret these results. So based on these results, it appears that the elevator, is relatively safe because there's approximately a 7% chance that the elevator will be overloaded using the given mean. So there's a 93% chance that everything would be fine. But remember, that mean was inaccurate. The mean that we were given was 174 pounds. I guess men used to weigh about 174 pounds. That used to be the mean weight of men. But these days, it's closer to 189 pounds. If the weight of man, if the true mean of the weights of men, is 189 pounds as opposed to 174, we're going to get a very different number for the probability that X bar is greater than 185, which is what the problem was asking us to find. So using this dated mean of the 174 pounds, it makes the elevator appear to be very safe, but it may not be that safe. It might make more sense to use this mean of 189 pounds. If we use the mean of 189 pounds, we might find that it's not safe at all. So you might want to repeat this procedure using the true mean of 189 and consider whether the design is truly safe given accurate population data. So let's do this again. This time I want to use a mean of 189. So we'll do norm.dist, got 185 as my X value, the mean is 189, and the standard deviation still is that 7.51 approximately. And then that's the area to the left. I want the area to the right. So it's actually a 70% chance. Do you see that difference? There is a 70% chance that that elevator will be overloaded as opposed to a 7% chance. So when we use the dated data, it looks like the elevator is fine. When we use the accurate data, it looks like 70% of the time the elevator is going to break on us. We're going to have problems. So it's really important that we use that accurate data. If it turned out that there's only a 7% chance that the elevator is overloaded, but it continued to break, the elevator's having issues every time a number of men get on the elevator, it just keeps breaking and breaking and breaking. And there's only supposed to be a 7% chance that that's happening, but it's happening a lot more often. We might say, well, our assumptions must be incorrect. And maybe the assumption that is incorrect in this case is that the mean weight of men is 174 pounds. I think, I'm not 100% sure about the history, but I have a feeling that something like that probably happened, because you've got this mean of 174 pounds, which implies that everything is safe. But then if it turns out that that elevator is breaking all the time and it's not safe, maybe the assumption that happens to be wrong is that the mean weight of men is 174 pounds. Maybe they found out that that mean weight of men was inaccurate, and when they found the new mean weight of men, 189 pounds, they could be much more accurate and design a much safer elevator. So that is the end of our discussion of the rear event rule and the central limit theorem. Again, the central limit theorem is allowing us to compute these probabilities, but the rear event rule is aiding us in the interpretation of these results. So yeah, the rare event rule is what I applied here when I said if there's a 7% chance that that elevator is overloaded according to our statistics, but then it keeps happening and it keeps happening and it keeps happening. Well, maybe the assumption that we started with is wrong, the assumption that gave us that 7% chance. And it turned out that the assumption that the mean weight of men is 174 pounds was wrong. The mean weight of men is actually a little bit higher. It's 189, which means that the elevator is much more likely to be overloaded.